Elasticity and springs. Every solid object will stretch, compress, or deform when a force acts on it. A restoring force or spring force is a force that will restore a system to its equilibrium position. For example, if you smush into your face, you're going to deform your face by applying a force with your fingers as you smush it. When you let go, your face goes back to normal through its own restoring or spring force. Any system that has a restoring force is called elastic. Basic examples are springs and rubber bands. Here's an example of a spring. You can see that this spring right here is at equilibrium or rest, and that as you apply a force to the spring will pull back with an equal and opposite spring force. A spring at rest is said to be at equilibrium. If you compress or stretch a spring, it can store energy, which can be used to do work. You can see that this person here is stretching the resistance band as they exercise, and in doing so is storing energy inside the spring. If they were to let go of this resistance band, it would snap down and probably hurt their feet. But if they were to let go, what you would see is the conversion of the elastic potential energy in their hands to kinetic energy as it snaps back down. And that shows that there's energy stored inside the spring rubber band. Springs are unique in that they have a variable force, which means they're harder to pull the farther they are from equilibrium. For example, pulling this resistance band this far does not take as much effort as pulling the resistance band this far. They're harder to press the farther they are. Another example is blowing up a balloon. Balloons are elastic, and as you blow up the balloon, it hurts your cheeks more and more to apply more and more air because there's the force of the balloon increasing. Another example would be playing guitar. As you pluck the strings, the farther you pluck, the more force it requires. Hooke's law says that the spring force is proportional to the displacement of the end of the spring, meaning that as you approach a spring at equilibrium, that as you compress the spring, it'll require more and more force. You can see in this picture that this spring is storing energy in the form of potential energy and using that to convert into kinetic energy, sending the block flying away afterwards. This is the equation for Hooke's law. And you can see that the equation sets up the relationship between the spring force and the displacement of the spring. In this equation, F specifically is referring to the restoring force, not the force that you apply, but the restoring force of the spring pulling back. So if this is your spring and you apply a force to the spring to pull it downwards, the spring is going to resist in its own fashion upwards. That's your spring force right here. Since the spring force is in the opposite direction as the applied force, that's why the equation here has that negative, because you're pulling in one direction and the force is in the opposite direction. The letter K right here is referring to the spring constant. The spring constant is what you might consider to be the springiness or stiffness of the spring. If you have a large K, that means it's a really stiff spring. If you have a small k, that means it's a squishable spring. The letter X right here is referring to the amount of compression. So that's this right here, the distance that you compress it or extend from equilibrium. Let's use this equation to solve some problems. We have a force of 50 newtons applied to the spring, and the spring is going to stretch a distance of 5 centimeters, or 0.05 meters. We want the value of the spring constant K. It's important to notice that this is the force applied to the spring, which means that the spring force is going to be in the opposite direction, the same amount. So that's negative. And that's why we can say F equals negative Kx. We'd have negative 50 equals negative K times X. And that would give us our value of K, 1,000. The unit for K is Newton meters. which comes from the idea that if you were to get K by itself, that K would be a force over a distance, which is a Newton over a meter, which is why our units is Newton over meter. So next, the same spring with the same K value is placed horizontally on the table and stretched a distance of 11 centimeters. What force would be required to stretch the spring this amount? And I determined that the force would be 110 newtons, noting that this is the force of the restoring force of the spring being negative. So that means the force that you have to apply would be the same value, only positive. Remember that the value changes, either negative or positive, just referring to whichever direction it's pointing in. So since the spring force is in the opposite direction as the applied force, that's why the spring force is negative and the applied force is positive. For a force displacement graph, the slope K of the line is called the spring constant and has units of Newton meters. What makes the slope of the line K, you might ask? Well, we're going to be graphing things with force on the y-axis and distance on the x-axis. And the slope of any line, you might remember to be rise over run. So in this situation, the rise would be force, the run would be displacement. And the slope of the line, you might remember F equals K times X. If you were to get K by itself, it would be F over X. So that means that the slope of the line right here, F over X, would equal K. So we know that K is the slope of the line. But next, we're going to learn that work is the area under the curve. What makes work the area under the curve? If you think back to this type of situation, which is pretty much every object that a force has been applied to up until now, like for example, if you're like applying a force to a block and like pushing the block across the table, you're applying a constant force of like, let's say 50 newtons, and every meter you move it, it's still a force of 50 newtons. So that's why this graph right here is a straight line. The area under the curve right here is a shape of a rectangle, which is base times height. The base being position and the height being force. And you might remember that force times position is equal to work, or a change in energy. So that's why work is the area under the force curve, and that's why the equation for work for a normal situation is just force times distance. But when you have a spring, remember that as you pull on a spring, that pulling a spring this distance is way different than pulling a spring this distance. The more you pull a spring, the more effort, that's sweat right there, the more effort it's going to require. So that's why this force right here has an upward slope. And you can see that the shape of this is a triangle, and the area of a triangle is 1/2 base times height. Base being, of course, position, and height being force. However, we just learned that the force of anything as a spring is K times X. So that's why we can substitute this force as K times X multiplied by the base X, which would give us 1/2 kx squared. So that's why we can say that the work or potential energy is the area under the curve, and that it equals 1/2 kx squared. These are the two most common methods of determining work. If you have a variable force and your graph looks like this, you would have to use calculus to determine the amount of work or energy. So in summary, since this axis is force, or K times X, and this axis is distance, or x, we can say that the area under the curve is 1/2 kx squared, which is equal to the elastic potential energy stored in the spring. In this picture, the red line here shows theoretically what the line would look like for force versus elongation. But in real life, a spring doesn't act like that. In real life, you can compress a spring until it can't compress anymore, at which case it stops compressing. And in real life, you can extend a spring until it breaks, at which case it stops extending. So just know that this, the fact that we're describing this line as straight is just theoretical. In real life, it is not straight. But for the portion that is, this equation works. Here's our first question. The restoring force of 3 springs is measured as they're stretched. Which spring has the largest spring constant? Do 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 do. You're right if you said A. Remember that spring constant K is the slope of the line. So this has the highest slope, meaning it has the largest spring constant. In this next problem, it says that the spring has a constant of 125. What is the force required to compress the spring a distance of 13 centimeters? The spring force I calculated was 16.25 newtons, which means that the force that's required to pull would be positive 16.25 newtons. Next, it says how much energy is stored in the spring. Energy is 1/2 kx squared, and I got 1.1 joules. Here it says that you have a block on a surface. So like here's a spring, here's a block, and you're going to push the block into the spring. So as you push it, the spring is going to compress. Here's the block with the compressed spring. When you release it, the block is going to like fire away into the distance like this. So you can imagine that all of the potential energy stored in the spring before is going to be transformed into kinetic energy after. So if we have the potential energy of the spring before equaling the kinetic energy after, we can say that 1/2 kx squared will equal 1/2 mv squared. Using the variables from the problem, we can fill in our k, our x, and our mass. We can use that to find our velocity, 1.26. In this next problem, we have a 2-meter tall deck with a spring. The spring has been compressed and is going to release and launch a ball like a projectile, like this. We know that the ball has a mass of 1, the spring has a constant of 135, and its amount of compression is 25 centimeters. So let's find the velocity of the ball after it leaves the spring, knowing that the potential energy of the spring before is going to equal the kinetic energy of the spring after. And after filling the values, I got a velocity of 2.9. So knowing that it's been launched horizontally this way at 2.9 meters per second, we are going to use our kinematic equations. You might remember these charts from like months ago. So here we have the ball being launched horizontally at 2.9. Since there's no force horizontally, it's not accelerating horizontally, meaning that its final velocity is 2.9 as well. In the vertical direction, we know it's falling 2 meters at a rate of 9.8. And since it's been launched horizontally instead of being launched like upwards or downwards, we know that this initial velocity is going to be 0. And we are looking to calculate the horizontal distance the ball travels. You might remember that we can't calculate that without finding the time. So I'm going to find the time in the y direction first. So I'll fill in that's falling -2 1/2 -9.8 t squared. And I find the time to be 0.64. I'm going to use that to find the horizontal distance in the x direction using the same equation. So we'll find that that equals 2.9 times 0.64 plus 0 to find a total change in position of 1.9 meters. Next, we have a spring with a constant K being used to pull a 25 Newton block horizontally across the tabletop. I forgot to say at a constant rate. And it looks like there's friction on the tabletop as well. So I'm going to draw a sketch. Here's a person pulling a block across the tabletop. If we were going to turn this into a free body diagram, there would be a force gravity. It says it has a 25 Newton weight, which is the force gravity, not the mass. Our force normal will be 25. And we're going to have a force friction acting backwards that's going to be equal to the force of the spring pulling forwards. So my first step is going to be to calculate the force friction, mu times force normal. The mu is given in the problem, and I get a force friction equal to 5 newtons, which means that my spring force is also 5. Using the value of K, I can use that to find the distance that the spring has been stretched, which is 0.04 meters or 4 centimeters. Nice work today, guys.